So welcome to our June LOF&BE webinar. I'm Sarah McAllister. I host these with Sam Manzello and Sayaka Suzuki. I'm very pleased to announce our speaker today is Dr. Chris Lautenberger. He is a fire protection engineer based in Northern California with experience in fire science, fire dynamics, fire modeling, and forensic fire reconstruction. I know him very well because we were grad students together at UC Berkeley. So he's got his PhD in mechanical engineering from UC Berkeley, where he majored in combustion and studied pyrolysis and solid phase combustion. He currently leads a project funded by the California Energy Commission to develop next generation wildfire spread and risk models. He has co-taught master's level courses in fire dynamics and fire modeling at the Department of Fire Protection Engineering at California Polytechnic State University in San Luis Obispo. So with that, Chris, I'll let you go ahead, share your screen, get started, and I will make sure that everybody's admitted from the lobby and muted. So go right ahead.
Okay, well, thank you for that introduction. And let me just get my slides up here. I'm going to do kind of a hybrid approach today. I'm going to use some slides and I'm going to do some kind of live demo stuff. And as Sarah mentioned, one of the projects that we're currently working on is funded by the California Energy Commission. And the focus of that project is to develop next generation wildland fire spread and risk models. It's a 5-year project that started in 2019. And so we've been working on it for about 2.5 years at this point, with a few delays due to the pandemic. There's a lot of moving parts here. There's 4 main working groups to this project that we kind of got tired of calling it the CEC project. So we came up with a name for this particular project and call it the Pyrogens project, or the Pyrogens Consortium. So Pyrogens is fire intelligence. There's this being a very large project, there's 18 different organizations that are on this project, and it's organized into 4 main working groups. The first is led by Janice Cohn and addresses extreme weather, things like weather station siting, fire archetypes in California, meaning what types of fire weather tend to lead to big fires. Work group 2 is led by Scott Stevens, and it's developing some of the fundamental fire physics that will underpin the next generation surface fire spread model that is being developed to replace the raw thermal model, which I'll talk about here in short time. The third work group is the one that I'll be talking about today. This is a near term, which means usually about 4 to 8 days preview of upcoming fire weather, fire spread for active fires, and risk for fires or risk from fires that have not yet ignited. And then this is a nice contrast to the long-term forecasting led by Leroy Westerling. And what this is doing is looking at fire on the landscape in the second half of this century, so nominally 2050 to 2100, and what fire intensity and burn probabilities look like then. And so I'm just going to be focusing on one small part of this project, but I did want to introduce that there is many other folks involved in this, working on some really cool things. And the outline here, there's really just 2 main parts. I'm going to start with an intro and show some of the use cases for the short-term forecast tool that we've called Pyrocast. And then after that, move into how does it work? What's under the hood? And I suppose if we have time, we'll wrap up with some discussion and question and answers. So jumping into the first part, which is the Pyrocast short-term forecast tool. There's quite a large team. There's a lot of folks involved in this, and I'm going to be showing off a lot of their good work. You'll see there's a range of specializations here, everything from full stack developers, computer scientists, to forestry folks that are using LiDAR to measure fuels. We have a utilities analyst and economist that is looking at some of the cost benefits for this tool. And then even a fire behavior analyst that is applying some of these things in the field. So I'll jump in. I'm going to kind of transition here from slides over to, if I can figure out how to do that, to a browser. And if you go to pyrocast.org, you'll see this nice disclaimer, which says that this is a work in progress. This is a essentially a beta tool. It's available on an as-is basis. Use at your own risk, etc. Terms of use and privacy policy at the bottom. Assuming you're good with that, hit accept, and you'll land on a page like this. And I'm sure everybody's used maps like this before, so if you have, it should be pretty intuitive. The scroll or the mouse wheel scrolls in and out. You can pan, zoom, etc. There's a few base layers that you can select starting in the lower left. So if you want to look at satellite imagery as opposed to the map view, you can select that. The one that I like to use is a hybrid that has the satellite imagery with roads and place marks overlaid. It's nice to navigate that way. This being funded by the Energy Commission, one of the things of interest is impacts to power lines or transmission lines. So one of the assets at risk layers here is transmission lines. This is from the HIFLD Homeland Infrastructure Foundation level database, and it's transmission lines in the continental US. And we're using this for a few different purposes, which I'll show in a little bit. One is the project, one of the goals is to improve grid resiliency. So if there are fires that can impact transition lines, that's something we want to know about because it has impacts on the availability of electricity in California. Given that the grid is all interconnected at this point, fires elsewhere can affect availability of electricity in California. And we saw this last year during the bootleg fire in Oregon, when the bootleg fire burned into a 500 kV electrical corridor. Power lines, although transmission lines not as much as distribution lines, can also be a source of ignition, especially during high winds. And so another thing that we're doing is modeling fires that start under power lines and then quantifying the impacts from those fires to assets at risk, including structures. So structures is another thing that can be toggled on here. This is from the database has various names. Some people call it the Microsoft Building Footprint Database, other the Bing database, but this is useful for looking at potential structure impacts. This is also an input to some of the modeling that I'll show off here in a little bit, where we're quantifying impacts to structures as an asset at risk. In terms of kind of real-time situational awareness, there's a few different things. One, which is particularly useful when there's a lot of fires going on, is the live GOES 16 satellite imagery. So this is showing what's going on right now, usually with a lag time of 5 or 10 minutes. And so you can see we've got some fire activity. These are all smoke plumes, of course, going on in the Southwest GAC, Southwest Coordination Center GAC. And we'll look at some of these here in a little bit. Not a whole lot of fire activity in California right now. There's some ongoing fires, but they're largely quiet. We have some additional data here. MODIS and VIIRS, these are sensors, different sensors on 4 different satellites, and these are showing recent hotspot data. So we'll talk about this fire here in a little bit. But this gives you an idea of where the fire line is active. And we have also polygons or perimeters for current season fires. And so that's what this is showing. This fire is the Calf Canyon Hermit's Peak fire. For example, this is the Midnight fire. So these are updated as the data become available. These are all pulled from publicly available data sources. And we try to keep them current, or at least as current as we possibly can. There's some other real-time situational things to have a look at. You're probably aware of the Alert Wildfire camera system. And each of these cameras is a separate feed from Alert Wildfire. So if you were to pick one, this is probably not the most interesting one. Let's find one by a fire. Here's one by the Rancho fire. And you can see here at least if I make this window a little bit bigger, that this is from today at 1611. So this is what's going on right here, looking down at the Rancho fire. If we turn on the hot spots here, we're probably going to see there was a little bit of fire activity, but not too much. And so this suggests that they have this more or less buttoned up and under control, and this Rancho fire is probably going to be put out. One of the nice features of this is you can, just like in Google Earth, get a 3D view. So I've just transitioned to 3D terrain. Oops. And I'm going to, well, let me try that again here. That's better. Going to try to position the camera in the same view that we see in the real-time feed from Alert Wildfire. So here's an example of that where we can see where the camera is. This Eagle Peak is going to be this right here, and then we're looking off in the distance toward that Rancho fire, which is pretty quiet. So a few different ways to monitor conditions in real time. And what I'm going to do now, I'm going to switch over to, this is a development tool. This has some stuff that's not quite ready for prime time yet because we're still working on it, but it will be deployed to the production site here shortly. So one of the things that has a big impact on current fire spread is where past fires have been. And so this is a layer that shows past fire history broken out by, I think we have the last 30 years in here, if I remember well. And so if we take, for example, the pipeline and the Haywire fire, this is just north of Flagstaff. And this is the one that just made a big run yesterday under pretty high winds. You can see there's been a lot of fire in the area in the last couple of decades. And one of the things we can do is look at where the current fires are relative to those past fires. So you can see the arson fire that was this pipeline fire yesterday, which started somewhere down around in here. Maybe it was 2 days ago. I can't remember. It all runs together. This is the perimeter, burned right through a 12-year-old fire, didn't even really slow down all that much. It burned into the back end of the Telegraph fire. This is a fire from April in this year. And then this Haywire fire started the same day or the day after the Telegraph fire. So this is a pretty complicated thing to model, which I'll show here in a little bit, because we have all this fire history, different ages, different levels of regrowth. And so the fuel inputs here are really critical for getting fire spread in this area right. And so what I'll do, I want to talk a little bit about the fuels inputs here. So if you look at the top here, we've got 4 different tabs. I'll go to fuels here. And why don't we go to California, and I'm going to turn off the fire history and show what we're looking at. So these colors here, and by the way, this is Landfire 2.2.0, which is also known as Landfire 2020, meaning it has disturbances, which is fires through 2020, but not through 2021. And these different colors here represent different, in this case, we're looking at the surface fuel model. So you could query a particular location, and it tells you it's timber understory 5 at that particular pixel, which is a pretty typical fuel model for, in this case, the Sierra. And you'll note a few different things here. So this is, you might see this kind of stand out. That's the burn scar from the King fire, which was a big fire back in 2014. That was really a very intense fire. That area is still a long way from coming back, and so you can see it reflected in the surface fuels down in the Rubicon Valley there. Another input that we use is, let me just show why we use this. If we turn off the fire history layer, you can see this is the Caldor fire, which probably most folks are familiar with from last year. That's not reflected in the Landfire fuel inputs. But if we go to the 2022 California Fuelscape, it is represented. So you can see that the effect of that disturbance from last summer is now reflected in the fuel inputs here, and that we have different fuel models assigned. Now, this is a layer that is produced by Pyrologics, by Joe Scott and his team. And I'll talk about this in a little bit, but we use the California Fuelscape for all modeling inside California, and then stock Landfire 2.2.0 with a correction or a burn-in for last season's fires in the rest of the US. So that's kind of the default fuel inputs here. There's a few other options that are incorporated into the modeling. One is a California-specific layer produced by Salo Sciences, or the California Forest Observatory, and they are using AI, LiDAR, and high-resolution imagery, satellite imagery, to map fuels at much higher resolution than is currently possible with Landsat 8 based products like Landfire, which are 30 meters. So the California Forest Observatory stuff is all 10 meter. This is 2020 era data. We're waiting on a 2022 update, which is going to include the millions and millions of acres that have burned since 2020. And you can see there's a lot of differences here between say these 10 meter canopy height data at 10 meter resolution. And if I flip over to say Landfire, you can see it's a lot more pixelated. The representation of roads is a lot different at 10 meters than at 30 meters. That makes a big difference. If we look at an area that was burned over in the Caldor fire, destroying many, many structures, let's do that. I can turn on structures, and let me dial back the opacity. So this is an area called Grizzly Flat. It was basically destroyed by the Caldor fire under a combined wind-driven, plume-driven, or fuel-driven fire. And if you just look at, say, the 10-meter inputs from Forest Observatory, let me dial up the opacity. There we go. That, and actually canopy height isn't the best. Let's use canopy cover. Yeah, canopy cover. So this is 10 meter description of canopy around the structures. And then this would be our default. Let me go to Landfire. That's what the description of the canopy looks like in the 30 meter fuels. So you can see what we're currently using as default in 30 meters is okay, but it's got a lot of room for improvement. There's some really great high resolution products that are coming, at least for California and possibly for other parts of the Western US, that should really improve modeling in some of these areas where there's a lot of wildland urban interface. These pixels that are showing through, if I didn't mention this, anywhere you can see the background is because those are marked as non-burnable in Landfire. Those are roads and things like that. So one of the things that we're trying to do here is make available all the inputs. So if you want to, and I'll show some of the forecasts here in a bit, if you want to look at a particular area and understand what is the fuel model, what is the canopy base height, what is the canopy bulk density, all these things that go into fire spread modeling. The data is all right here, and as I'll show in a little bit, it's also available for download by API and also download of the raw data files themselves. Okay, so that's the fuel tab, and we also, of course, need to know something about weather to be able to forecast fire spread. So I'm going to switch gears and go to the weather tab here. I'm going to pop back to the production site actually before I do that. And there we are. So this is the first temporal layer that we've had, meaning this is the first time aware layer that you have. So I should introduce that there's a time slider down here, UTC and local time. So 5 p.m. PDT or 12, I guess it's 00 UTC. And it's going to be really hot in the Midwest this weekend. or not this weekend, this week, back today and tomorrow. And so there's a few different ways to visualize this data. The first is what I'm doing here, where I just hit play. You'll see this pulsing. It doesn't. It's not the most aesthetic in the world, at least the first time it plays. But then if you go back, you can move that slider, and things are pretty smooth. So this is just looking at temperature. Wanted to introduce the time slider. One of the nice things about this is you can query any particular location using this query tool in the upper right and get a time series of what, in this case, the temperature is forecast to do at that location as a function of time hourly for the next 8 days in this particular case. So temperature, of course, is one thing. It's relevant for fire because it controls dryness of fuel, or at least it influences dryness of fuels. And there's some fire-specific things in here as well. So we have, I think we have a red flag warning going on now. Let's check that. So if you click this little red flag warning tab or icon, it'll show you where there's a red flag warning. And dial back the opacity so we can see that a little bit. So southwestern Colorado, northeastern New Mexico all have some red flag warnings going on for 20-foot winds, 20 to 25 miles per hour with gusts to 35. And so if we wanted to look at some fire metrics there, like a Fosberg index, if you're not familiar with the Fosberg fire weather index, it's a single environmental filter that combines relative humidity, temperature, and sustained wind speed into a fuel independent measure of potential for fire spread. So this is showing in this particular area, Fosberg index might get up to, looks like about 45 or 50. A rule of thumb for Fosberg is anything over 50 for 3 or more hours is of concern. There's some other indices that are used for fire weather purposes. So a hot, dry, windy index uses vapor pressure deficit in lieu of, or instead of, relative humidity. It's probably a little bit better way of getting at that drying force, or the force for drying, than relative humidity. And hot, dry, windy has different units. It's got basically hectopascals, which is the vapor pressure deficit, and then meters per second is the wind speed. And so any areas where that's about 400 or 500 or higher, that corresponds or correlates with rapid fire spread and ultimately pretty large fire size. So there's some good weather information here, some fire specific quantities. So another thing that's relevant, if we wanted to look at, say, let's look at fine dead fuel moisture. So this would be like 1 hour fuel moisture. And you can see it's pretty dry out there over, at least right now, over large parts of the western US. If we go out, say later a couple days out, we see some relief, at least for the eastern part. And it's under that big heat dome now, but the west is still pretty low fuel moisture. So in Southwest, yeah, fuel moisture is down around 2%, something like that. That's about as low as you can drive 1 hour fuel moistures. And some of the cool things that I find interesting, at least, is you can query some of this data and then look at it in 3D overlaid on the terrain. So if we go to, say, Death Valley, where it's going to be really hot, say at Furnace Creek, where the Ross station is, forecast to get up to almost, yikes, almost 120 later this week. And there, we can dial that in. And so that's the lowest spot in the continental US. And then not too far away is the highest spot in the continental US. And so we can look at the difference in temperature in, say, Death Valley, which, what did I say, it was forecast to be over 100, 110. And then just barely 100 miles away, up on top of Mount Whitney, it's going to struggle to hit 55. And so looking at the, the temperature, you really get the, overlaid on the terrain or the topography, you really get the idea of how that topography is influencing temperature. I had to use temperature as an example because there just isn't that much wind going on. Usually we would be more interested in how topography is affecting wind, but I think you get the idea. So that's that's the weather pipeline here. I'll talk about this in a bit, but there's 3 models that feed into this. They're updated every 6 hours, 4 times a day. And this is then used, the data that's pulled in from the operational weather models to calculate fuel moistures, both live and dead, and then that feeds into the fire forecast stuff. And I'll talk about that here next. So we have really 2 main forecast tabs. The first is for active fires, which is what you'll see when you land here. And I'm going to just refresh this and zoom in. Let's look at a fire or 2. So you can tell pretty quickly where things are happening by the smoke plumes. So here's one, and we know that that's the Calf Canyon and Hermit's Peak fire. This is in all likelihood a burnout operation, although I don't know for sure. But when you see features like that, probably what is going on there is fire line was built, and then this was fired out to bring this flank into the main fire so that there's black there. I don't know that for sure, but that's certainly a strong possibility, and it's putting out a good amount of smoke today. Up here is the let me turn this off. That's better. The midnight fire. And so if you click on one of these icons that has the fire name, you'll see something that says, click here to view forecast. And then I'll call your attention to this left panel over here. So we've got the fire selected. This is the midnight fire. And then there's this predicted fire size. There's different percentiles. I'll explain what that is. This tool or this platform is built to be model agnostic, meaning whatever the current fire model is that works the best, we can plug that in to this system. So currently the model that's being used is LOF&BE, which is Eulerian level set model for fire spread. It's a model that I've been working on for some time now. And grayed out is GridFire. GridFire is a similar model developed by a spatial informatics group that we're in the process of incorporating. And so what this is doing here is just moving forward in time, and I'll go to local time. So this is 2 days from now, if I have the date right. Yeah, it's the 14th. So this is the modeled fire perimeter 2 days from now, roughly. So we can go out to about 5 days, and these fires are modeled as unsuppressed, which means they're almost always over-predicted, except for the case where there's no suppression or winds are such that the fires are basically unsuppressible. So what this is showing is this gray area here is the modeled fire spread 5 days from the initialization time here, which was this morning at 10:49 Pacific, 10:49 a.m. Pacific. That was the last bit of hotspot data that went into this. And going back to the starting condition, this blue here, and I'll move it up next to the legend. Blue is areas that burned before the start of the forecast, so they're cold. Purple is areas that are burning at the start of the forecast. That's determined from satellite data, infrared imagery, etc. And so what you'll see here is that the fire is only spreading out from those purple areas. Okay, it's not spreading out from the blue areas because those are cold. Those are already burned. And there we go. So this is one particular forecast. These models are run as ensembles. So there's a lot of uncertainty and variability here, both in the inputs, as well as some of the underlying spotting algorithms, including spotting, which is heavily stochastic. So you can see here, we've got a wind out of the south and there's a spot fire forming out in front of the fire. There's no way to predict where that spot fire will form or if it will ignite. And so these are run as ensembles where there's between 200 and 1,000 perturbations of the baseline inputs, as well as the stochastic parameters that control things like spotting. That's the big one. And what that does is it leads to a distribution of fire sizes. And so when it says predicted fire size, median is 50th percentile. If we were to go to the smallest, that's the 10th percentile fire size. So that's out of these hundreds of ensemble members. That's the, say we did 1,000, this would be the 100th smallest fire. And conversely, if we were to go to the, say the 90th percentile, that's kind of like a worst case. That's usually an over prediction and often a gross over prediction of the spread. But the nice thing about this is self-calibrating, or can be used for self-calibration purposes. So if you know your model from yesterday under predicted, then it's likely that your model from today will also under predict. So instead of using the 50th percentile as kind of the best guess, you might want to use the 70th percentile, which is going to be a little bit bigger. Okay, so these are this is a really important part of the way that fires are being modeled. Is there's not just one forecast, but there's hundreds, sometimes thousands. And you'll note here we have a few different forecast start times. So this is today at 10:49 Pacific. There's a few other start times in here, and those are all going to look slightly different. And it just depends a little bit on where the hotspot data comes in from the satellite. So in this particular initialization, you can see this blue area is already burned. These hotspots here are outside of the perimeter. So these came in after this forecast start time, which was yesterday morning. Whereas if we go to this morning's forecast start time, there's now new hot spots here. And so this part of the fire perimeter was hot at the start of the forecast. So there's a lot that goes into initializing the fire from the satellite data, and then using the weather data to calculate fuel moistures, et cetera, and then drive fire spread forecasts with that. So we can go to maybe a fire that has some potential to impact structures, just hopefully it doesn't, but this has been a pretty damaging season already. We talked before about the pipeline and the haywire fire. So I'm turning on here all the hotspot data. So this is the new fire. This is the pipeline fire. This is the haywire fire. And then this is the old fire. This is the telegraph fire. And so this is a real challenge, especially when you consider all the past fire history in here to model. But let's take a look and see what we have. So if we select the pipeline and haywire fire, I'm going to turn off some of the modus and veers. So for this initialization, everything in purple is burning. This blue is already burned. It's now cold, at least in the model. And we can drag this forward in time and maybe look at, let's go to Satellite Street, look at some structures. So there's some structures out there, but it looks like it's burning into a pretty remote area. And if we were to go to, say, the 17th, so this is 2 days from now, no, sorry, 3 days from now in the afternoon. So this is the modeled unsuppressed fire spread for this particular fire. Okay. Let's see, I talked about percentiles. Oh, I should mention that the ultimate goal here is to have not just different models that one can select, so elm fire, grid fire, coffee, which is a coupled atmosphere model, is in the works, but also different fuel inputs, right? We're using the Landfire 2.2.0 here, but there may be other products, that are available at some point in the future. So the idea here is to build really a framework that works with different models, different fuel inputs, and allow the user to select which data they're interested in. Okay, so that's active fires. The other part here is risk, and you could probably argue that this isn't actually risk, but it's something else related to probability or possibly consequence. And here what we're looking at is potential impacts to power lines, as well as fires spreading from power lines and impacting assets at risk. So let me back up here a little bit. Starting at the top, we've got two ignition patterns. We've got human-caused ignitions and then transmission lines. I'll show those here in a little bit. What this is doing is igniting a couple 100 million fires across California on a daily basis, every hour for the next 5 days, and then quantifying their impacts to assets at risk. The ignition pattern is based on historical fire occurrence. So areas that have seen lots of fires historically see more fires in this large-scale Monte Carlo simulation than areas that have seen fewer fires. Also, dryness is taken into account. So as the fire season ramps up, we'll see more and more fires start to occur because of that. It's dryness, but it's quantified in terms of the energy release component, specifically ERC percentile. All right, so the quantities that we have here are, let's start with fire area. So what this is the modeled fire area for a fire starting in a given area as a function of time. And let's move forward to, so here we are, this is 5 p.m. today. That red looks a little scary, but it's not that bad relative to some of the other times of year. So I just queried a location, and what that's saying is that, let me back it up to earlier today. So for this particular area here, the modeled fire size after 6 hours is about 3,500 acres, which is not unreasonable given the dryness out there at this early point in the season. And so we can also look at, say, the relative burn probability. So what that's showing is the areas that are more likely to burn. Oh, I have the opacity back, that's why. Areas that are more likely to burn than others based on the combination of fuel, weather, topography, and historical fire occurrence. And if we were to look at the number of impacted structures, this is oriented back to the ignition location. All this is back to the ignition location. So what this is showing is basically areas that are redder are worse, are more likely to have fires that result in structure losses than areas that are green. So this area here south of Highway 12, if we were to just take a look at it, see why it shows up. Well, we've got a lot of structures there. Some fuel, some shrub, probably a lot of grass. And so the model's picking up on that as an area where if there is an ignition, it has a potential to impact structures. Now, impacted structures don't mean destroyed. It just means that the fire perimeter burns into an area where there's structures. So this is used to map on really a daily basis. These models run once a day, sometimes twice a day, pulling in current forecast data, fuel moistures, et cetera, and are looking at where there are potential impacts to assets at risk. So that's for the kind of historical ignition pattern. The other thing that we are doing, really more as a demonstration than anything else, is modeling fires that start under, in this case, transmission lines. If you look here, you can see there's certain areas where, okay, I guess this is impacted structures. Let me go back to fire area. So what this is showing is for these hundreds of millions of fires that are ignited underneath transmission lines, the fire size as a function of time, this is for 6 hours of fire spread at different points in the future. So why don't we pick, this is an area not too far from where I live. There we go. So this is saying potential for about 1,500 acres after 6 hours for a fire starting at, I guess that would be today at 2 p.m. And looks better for the rest of the week, going out about 5 days. If we were to look at, say, the number of impacted structures, we can see some kind of hot pockets or some some areas where there's potential for upwards of 100 structures to be impacted. Turning on the structures layer, you can get an idea of why that's the case in this particular area. And if we were to look at, say, the relative burn probability, what you can see is fire coming off of that line under a west wind impacting those structures. You'll see there's a login area here. This is where customers can add their proprietary and confidential data. So this is what we're looking at here is using all publicly available data, and this is the HIFLD transmission lines. But really the more important, I don't know if it's more important, equally as important would be distribution lines, which are what gets into neighborhoods. Transmission lines tend to be a little bit more resilient to fire starts than distribution lines. And so for the kind of cordoned off, firewalled side of things, clients have the ability to add their own assets and use that for things like informing public safety power shutoff decisions. Okay. I think I got to the main things that I wanted to get through here. I guess the last thing I wanted to show as far as a demo is how do you get to this data? Well, there's a few different pathways here. There's of course this web application that we've been looking at. If you're wanting to get at the raw data, you navigate to data.pyrogens.org, and this is just a pretty vanilla web server that has anything that we were looking at in the web application is available here. So for example, if we were to go to the fire spread forecast, here's all the forecasts for the individual fires. Pipeline, Rancho was that one in Northern California. So you can navigate through this folder. These are the different initialization times. That's the model, that's the fuel. And then these are the different percentiles, spread percentiles. So that data is all there, including all the fuel inputs, all the static layers. If you go into, say, fire weather forecast, here's the underlying fire weather data. These are raw geotiffs. So we have several folks that are scraping this data, meaning using command line tools, scripts, wget, things like that to just pull this data down and either use it for real-time situational awareness or archive it for later use. A lot of customers would prefer to use a API. And so if you go to data.pyrogens.org/geoserver/web, you'll see this thing over on the right that provides web map services. And so if you're to say copy this URL for WMS, which is web map services, copy link address, and then I'm going to have to get open QGIS here. So WMS or web map service tiles are a really easy way to import data into your internal ecosystem. And I happen to use QGIS, which is an open source, freely available GIS tool. A lot of other people use Esri, but regardless of your choice of software, you can pull the data in the same way. So if I were to go add layer, add WMS, Web Map Services layer. Just create a new one. Paste that URL. I have to give it a name, don't I? I'll say demo. Paste that URL in if it's still on the clipboard. You go OK. And I think I should click connect. And then what it will do is query the GeoServer and find out all of the information that it has available so that it can be pulled into QGIS or Esri or whatever. So for example, if we were to go to, I don't know, why don't we do a fire weather layer just for fun? And I'll search for TMPF, which is temperature in Fahrenheit. And so here, this one looks as good as any. So you would just select that layer that you want, say add, then click close. It's going to pull this over the wire. So now QGIS is talking to the GeoServer. And if all goes well, we should have here in QGIS this temperature layer. So it looks just like it does in the web map, except now rather than in a web application, we're in GIS. So you can pull in whatever layers you want. So here's a base layer, Esri streets, for example. And if we wanted to pull in some fire data, which is probably a more typical use case, the same thing applies. So you'd go add layer, add a WMS layer. If we wanted to do, why don't we do a pipeline fire forecast? We'll go to a 50th percentile burn probability, or fire spread percentile, I should say. And we'll pull it out for 4 days from now and go add. Okay, close. It's going to think for a bit, pull some data over the wire, and we can zoom to this layer here, turn off the temperature layer. And we've just pulled that pre-styled perimeter into GIS. So there's a few different ways you can get at the data, whether you're just using the web app or want to pull in the raw data files or use an API. It's all there. So looks like we have about 10 minutes left. So I thought this might happen. I'm certainly not going to be able to get through a lot of the slides that I had. So let me go back to the second part here, see if I can hit some of the highlights, and I would like to just save some time for discussion. I went over most of this. I really just wanted to kind of get into some of the details for where the data comes from. If anybody's interested, I'd be happy to share this. But these are the operational weather models that are used to pull in the weather inputs. This is where the near real-time fire inputs come from. It's a combination of data feeds from CAL FIRE and National Interagency Fire Center, standard sources like NASA firms, a couple other things. And the models I mentioned briefly is LOF&BE. There's also GridFire, the model developed by SIG, a bunch of math, and we don't need to get into details. Oh, one of the things that's an important consideration I should just mention is live fuel moistures. This is a real challenge in fire modeling. We're currently using the NFDRS 2016 system, which is based on the growing season index concept and vapor pressure deficit. Hasn't really been tested all that well. We've done some comparisons to what's in the National Fuel Moisture Database, and it seems like it works well in some cases. In others, it doesn't. But this is what we're currently using is NFDRS 2016, and I think there's a lot of work that could be done to improve some of the kind of the live fuel moisture components of the modeling. So just in the interest of time, I'm going to skip over a lot of these kind of more mathematical stuff or mathematical things, and maybe I'll wrap up here, Sarah, and stop sharing my screen in case there's any questions or comments. I'd be happy to do my best to answer any questions folks might have.
Yeah, awesome. Thanks, Chris. This is a like a really cool tool to have everything all at once in one place. So yeah, if anybody has questions, feel free to type them in the chat or just unmute and speak away if you're okay with being up on YouTube for free. While we're waiting for that, I'll start, by asking my questions. Host's privilege. So I mean, so you mentioned that if you were a user that had sensitive data, you could create a login and add your data there that nobody else would see. But otherwise, do you need a login or credential? This is all just freely open, available for whoever wants to stumble on it and use it.
Correct. Yep. Yeah.
Awesome.
The only confidential data would be for customers or clients, typically utilities that want to start fires under their power lines and use that for public safety power shutoff purposes. But everything else, it's all publicly available data pulled from a lot of widely used sources, and one of the goals here is really to just create the framework and kind of the architecture, and then really improve the modeling capabilities over the next several years. I didn't really even get into kind of the next generation parts here, but there's some really cool things going on with regard to modeling suppression. That's a big one. We are beta testing a suppression model. There's a couple other things related to spread in the wildland urban interface. The models don't do that very well, if at all, currently. And then also the fire atmosphere coupling work in terms of integrating coffee. Those are some of the kind of next generation developments that are kind of currently underway. At this point, we have, I would say, a next generation platform that we're plugging in kind of current generation spread models into.
Yeah, that's fair.
But,
Yeah, I mean, because as you're going through your slides, it seems like Rothermel is a lot of the basis, and you're using wildland fuel models, and yeah, that obviously kind of falls apart when you're trying to look at spread into the community, right?
yep, Tubbs fire. Yes, a lot of those fires that burn through the populated areas, all those fuels are marked as non-burnable in land fire. And so in the fire spread models, they run up to Coffee Park in Santa Rosa and stop.
Yeah, and
And
then I'm
so,
done. Yeah,
yeah,
that's interesting. So I mean, the way that the fire models are instituted right now is all automated, right? I mean, like you don't have to, as a user, request it. It's these things are already just kind of run in the background, and you can just kind of view
yeah,
results.
the really the main thing that has to be done manually is add new fires. If something doesn't hit a list, so the two lists that we pull in are from CAL FIRE for fires in California, and then from NIFC, the NIFC large fires list, and that's updated once a day. So
Right.
there might be a fire with some high potential for spread that ignites on Tuesday at 10 a.m. and unless it's added manually, it wouldn't show up until Wednesday at 8 or 9 a.m. the next day. So we have a way to just basically specify coordinates, time of ignition, fire name, boom, and then it's added.
Okay.
So,
And then it'll start automatically pulling whatever it needs to run the models and all of that. Yeah.
yeah, and then the forecasts stay in the system long enough that you can usually go back after 2 or 3 days and see how well they did or didn't do.
Nice.
And with the, because you have that, at that point, you have the satellite data or the mapped perimeters or whatever it is. And so, that's a nice thing that kind of keeps us honest. We're trying to really
Yeah.
make things as transparent and open as possible. We want people to take the data, use the data, work with it, suggest ways to improve it. That's one of the reasons for putting it out there. An important part of the project that I didn't mention that I should have is the CEC requires all of this to be released as open source software. So everything from the spread models to the web application will be released under a copyleft license, which I won't get into too many details. But basically what it means is you can do whatever you want with it, but if you modify it, you have to release your source code too. So it's a viral license. That will be done before the end of the project. In all likelihood, it might be done in the next couple of weeks. We haven't really figured it out. We ran into some challenges with people taking the software and not following the license. And so currently it's all on GitHub, but it's in private repositories, open to collaborators and things like that. So this is, this is really a step at developing some open source tools that could be used by others.
Nice. As we were chatting, some comments and questions have popped up in the chat box here. So Sarah Harris asks if you could please post the reference to the paper you referred to on the fire spread model you developed.
Sure.
And oh yeah, Babak points out the Marshall fire was another one that just ripped through a community and was like barely a wildland fire before it was an urban fire. And
it
another
was more of, yeah, exactly.
I should have mentioned some grass
that.
Involved somewhere.
Very small, very short.
Yeah. So Daryl asks, is there any thought to going beyond a 5-day forecast of fire growth?
Yeah, actually, we have had a request from some users to go to 7 days. And so we can go to 7 days. In fact, I was earlier this year doing 7-day forecasts. The idea, one of the ideas would be to do a 5-day and then a 14-day. Although at 14 days, there's so many accumulating errors that you're really going to be pretty far off the mark. But currently we're set up to go out to as many as 8 days. And since the GFS, which is the long-range model, goes out to 16 days, we could conceivably do 14-day deterministic forecasts. But yeah, that was something that's been brought up by others as a need.
Yeah, I mean, it seems one of the big hurdles too is like the weather forecasts aren't very good past 3 days. So I think if you're manually doing it, you kind of have to go off of like climatic data, right? Because the weather forecasts don't go. So I'm sure that's a challenge with all of this too, right?
Yeah, so a little bit different approach than like what an LTAN would do and a long-term analyst would do in like FS Pro or within in WIFDIS. And I think there's some stochastic component to FS Pro and WIFDIS, whereas this is all deterministic. We don't treat day 14 any differently than day 2, or if we were to run forecasted 14 days, wouldn't treat day 14 any differently than day 2. It's all one weather stream, although the weather stream gets perturbed, but it's not doing any like historical climatology for looking out past whatever the near-term fire behavior is done in FS Pro.
I gotcha. All right, so one final question before we run out of time here is if there are any concerns around the public using these fire spread predictions, and if the model gets it wrong and they've made a decision on that prediction that puts them at risk.
Yes, that's why we have a disclaimer that says this is a work in progress, use at your own risk. I hope folks understand that this is something that will be improved. But I think getting the forecasts out there, just the way that hurricane forecasts, for example, are put out there, people can appreciate that. The models will give you a pretty good idea of where the fire is going, but people should always listen to first responders and follow evacuation orders, and not rely on a website with some modeling based on 50-year-old spread models, for example.
Yeah, gotcha. Well, and I feel like, I mean, this looks like a great tool for people who are kind of familiar with the lingo and how things work. But I don't know if like Joe Blow is going to decide whether or not to evacuate his house based on, because there's still some kind of knowledge into what does all this mean into being able to use it, right, to make those decisions. So
yes,
I think the people who will be using it are those that I hope to understand the context behind a lot of this. So with that, thank you again, Chris. That was an awesome talk. So just a reminder that we got another one coming up in July. So see everybody then, hopefully. So adios.
Bye, everybody. Thank you.